To evaluate such kind of integrals involving the sine theta, cosine theta, we always used to put z equal to e the power iota theta, right? So that we can get dz to be equal to e the power iota theta into iota d theta. So this is again z iota d theta, right? And also this cos theta can be written as it is e the power iota theta plus e the power minus iota theta divided by 2. So replacing this e the power iota theta with z. So this is z plus 1 by z into 1/2. So we have to put all these details into such kind of integrals, right? Let's start with the solution. So for this integral, we can change the sine square theta to be equal to 1 minus cosine of 2 theta divided by 2, right? So that we can have our integrand to be in cosine. So writing here 1 minus cosine of 2 theta divided by 5 minus 4 cos of theta d theta. Now by Euler's formula, we know that e the power 2 iota theta is equal to cos of 2 theta plus iota sine of 2 theta. So can I write this integral to be equal to real part of 1/2 of the integration of 1 minus e the power 2 iota theta divided by 5 minus 4 cos of theta, yes? Can I write like this? Real part of this e the power 2 iota theta is what? Only cosine of 2 theta, right? So we can write this above integral to be the real part of this integral. So let's use this. So this integral is equal to the real part of 1/2 into the integral 1 minus e the power 2 iota theta divided by 5 minus cosine of theta d theta, right? And now here we have to put z equal to e the power iota theta so that we can get dz to be equal to iota e the power iota theta d theta. This is again your z, right? And also we know that cos of theta is equal to e the power iota theta plus e the power minus iota theta divided by 2. So that will be equal to z plus z inverse. That will be 1 by z into 1/2. So let's put all these details for this integral, and this will be over the circle mod z equal to 1. So this is equal to the real part of 1/2 of the integration over the circle mod z equal to 1. This is 1 minus, okay, instead of e the power 2 iota theta, we can write this as z square, right? So z is e the power iota theta. So e the power 2 iota theta will be z square. So this is z square divided by 5 minus 4. Instead of cosine theta, I am writing z plus 1 by z into 1/2. And for d theta, we write dz divided by iota z from here, right? So 2 is cancelled out with this. So this is further equal to the real part of 1 divided by 2 iota. I am taking this iota outside of this integral. 1 minus z square divided by, when you solve this, you will be getting 5z minus 2 into z square plus 1 dz. This denominator will be further equal to minus 2z square plus 5z minus 2. And when taking the minus common, we get 2z square minus 5z plus 2. Making the factors for this, this is 2z minus 1 into z minus 2. So writing the denominator to be this. So this is minus of 2z minus 1 into z minus 2. If I take minus common from the numerator, I will be getting z square minus 1 in the numerator, and this minus sign cancelled out with this. So this is z square minus 1 in the numerator. Now writing the poles of the integrand. How to find the poles? We find the poles by taking the denominator to be equal to 0. And from here we get z equal to 1/2 and z equal to 2. So for the circle mod z equal to 1, this 2 does not lies inside the circle. Only z equal to 1/2 lies inside the circle. Right? So we are going to find the residue for fz at z equal to 1/2 only. Right? So let's write this. So we have got z to be equal to 1 by 2 and 2 to be our poles, out of which z equal to 2 lies outside the circle, mod z equal to 1, and z equal to 1 by 2 lies inside the circle, mod z equal to 1, right? So we have to find the residue at z equal to 1/2 only, right? The simple pole. So the formula for this is limit z tending to this point on z minus 1/2 into f of z. So this is equal to limit z tending to 1/2 into z minus 1/2, writing the complete fz to be this. So this is z square minus 1 divided by 2z minus 1 into z minus 2. So this is limit z tending to 1/2. This will be 2z minus 1 divided by 2 into z square minus 1 divided by 2z minus 1 into z minus 2. These two cancelled out? Yes. And when putting z equal to 1/2 in place of z, we get 1 by 2 into, okay, z square is 1 by 4 minus 1, and in the denominator we have 1 by 2 minus 2, right? So this gives further 1/2 into, okay, 1 by 4 minus 1 will be minus 3 by 4 into 1 divided by 1/2 minus 2, that is minus 3 by 2. So minus 3 cancelled out with this, 2 is cancelled out with this, and we have this to be 1 divided by 4 to be the residue at z equal to 1/2. So by Cauchy's residue theorem, integral is equal to 2 pi iota into the residue at z equal to 1/2. So this is equal to 2 pi iota into, what is the residue for this? It is 1 by 4. So that is pi iota divided by 2. And 1 divided by 2 iota is also multiplied with this integral. So we have to write that the given integral, that is 0 to 2 pi, the original integral, we have written this integral to be equal to the real part of 1 divided by 2 iota into the integral z square minus 1 divided by 2z minus 1 into z minus 2 dz. And we have found the value for this integral to be pi iota by 2. So now writing this value in place of this integral. Now the given integral becomes the real part of 1 divided by 2 iota into, writing the value for that integral, that is pi iota by 2, This iota cancelled out with this and we get this to be equal to pi divided by 4 to be the required solution for this integral. Okay, thank you.